All right, so welcome back to the fourth part of the talk. Okay, so the last section is a bit more advanced. It's going to be an application of some of the notions we saw before in computable structures. All right, so we're going to start by defining the jump of a structure. So trying to generalize the jump of a set, but now looking at structures. So the idea is the following. So the jump of a structure is it's going to take a structure and get another structure. And it's defined as follows. So you start with the structure A with some relations and some functions and some constants. And you're going to define this new structure, A jump, A prime, by adding infinitely many new relations, Rij. The J is the additive of the relation. Rij has additive J. And this tuple belongs to the relation if and only if A satisfies this formula where this is the this comes from an enumeration of all the computably infinitary sigma 1 formulas on the variables ij. So okay, so you take all the computably infinitary sigma 1 formulas. The j is the arity, so phi e, this is the if sigma 1 formula with arity j, and then you use Rij to encode that sigma 1 formula. Is probably you're right. Oh yeah, the I is equal to E. Yeah, thanks. That's what I meant. Yeah, good point. So this one, yeah. So the I here should be the same as the E there. But it's very easy to enumerate all the the sigma 1 computably infinitary formulas are given by a CE disjunction of finitary existential formulas. Right? Remember, it's an OR CE finitary existential formula. This is a CE disjunction, so you can enumerate all the CE sets. So you use the enumeration of the CE sets to enumerate all the computably infinitary sigma 1 formulas. All right? So that's what you do. So you add to A all these relations and encode all computably infinitary sigma 1 formulas the same way as when you define the Halting Green is said, you can put all the C sets in columns and encode all the existential sets of natural numbers. Now, instead of sets of natural numbers, you look at sigma 1 sets, sigma 1 definable relations in your structure, computably infinitary, and you just add them all. All right? So we call this one A prime the jump of A. This was defined independently. I guess the first definition is due to Ivan Soskov. I didn't know it. Like, my definition is from like 5 years later, but I didn't know of his definition. Putsarenko had a definition about the jumps of admissible structures, not structures in general. Ivan Soskov he even had like a couple of formulations of his definitions. All these formulations were different. Mine, Ivan's, and Pusarenko's. This is my formulation of the definition of the jump. The one by Soskov, he was adding a relation to force pi01 sentence. So he added this. So it wasn't that direct, but he added this relation of like forcing relation to the language, and then he noticed this kind of behaves like the jump, so this should be the jump. He called it the jump, and then he saw like this paper that I sent to one of these CIE, and then he has the same definition as mine, bro. And they are all equivalent up to even this notion of effective bi-interpretability. They are all like bi-interpretable in a very effective way. All these different definitions of jumps. I don't know what Putzarenko was doing with admissible sets, but Soskov, well, I guess he found this notion, I guess, very interesting because it had these nice properties and kind of behaved like it was a generalization of the jump. For me, it was a nice way of visualizing some results that already existed in computable structure theory. You could see it like from a different light if you use the language of the jump of structures. So that's why I liked it. And I was looking at some stuff with Boolean algebras, and it became, what was going on became much easier to see if you talked about the jumps of structures. There are two jump inversion theorems. Oh, I didn't put I think this one is due to Soskov. So okay, the jump inversion theorem, the usual one, generalizes to this type of jump. But when you generalize it, like into a larger setting, sometimes there are different ways of generalizing a theorem. And in this case, there are two different ways of generalizing this theorem. So I call them the first jump inversion and the second jump inversion. This one says that if you have any structure A, you can find a B that jumps to it. And this equivalence, so I'm going to not explain this very well, but this equivalence here is essentially, it can be like that, by interpretable in a very effective way. So they are essentially the same structure. Each one interprets the other in an effective way. So every structure you can invert. And yeah, I don't want to go too much into the details of the computability part, but for instance, you can imagine that you add to A zero-i relations that code zero jump. You can add zero jump to the structure A in some way. So one way of doing it, add an omega list of relations that code each, like nth relation code whether n belongs to zero jump or not. I don't know, or one ARI and they are true for everybody or false for everybody. But something that codes zero jump into the relation, but doesn't, I mean, something without any structure at all, just like this Turing degree information today. You could also state it for every A which computes zero jump, or like all the presentations of A compute zero jump, and then you can omit the zero jump on the right. And this one uses the marker extensions to prove that. The second jump inversion theorem, I didn't state it as a generalization of the second jump inversion theorem. The usual way to write it is that if you have x, this is in the Turing degrees, you have an x, and x computes a presentation of a jump for some structure A. Then there exists a y such that y jumps to x, and y computes a presentation of A. Not exactly the same A, but something that is isomorphic to A. So whenever this one computes a presentation of this, you can invert the jump on x, find something that inverts the jump on x, and computes a presentation of the original A without the jump. So there are kind of two different ways of generalizing jump inversion, and they are completely different theorems. And a corollary of this one is that the degree spectrum of a jump, meaning the set of all reals that compute copies of a jump, is exactly the set of all jumps of things that are in the degree spectrum of A. So it's a theorem that tells you, oh, we are in the right track. So it looks like the jump, kind of behaves like the jump. So this is kind of like the Turing jump, but generalized to structures. So a couple of examples, and this is kind of the reason that I started looking at it, which is different from theirs. In these two nice classes, and it happens in some other nice classes, so if L is a linear ordering, then the jump of L is equivalent, and again, in this by interpretability sense, to the original linear ordering together with the successor relation. You can add like the binary relation that tells you if an element is a successor of another, and something coding zero jump. These two are the same. So adding all the sigma 1 relations is equivalent to just adding successor and zero jump. And the same in the case of Boolean algebras, you get that all you need to add is the atom relation. So this is a kind of nice result that it tells you that the successor relation, I call it successor. Well, successor here is a pi 1 relation, so it's the complement of sigma 1. But it's kind of pi 1 complete. So if you add it, well, and zero jump, then you get all the other sigma 1 relations. You can compute all the others, up to computability in the sense of computable structures. So relatively intrinsically computability, or computably infinitary delta 1 definable. Up to that, if you add the successor, it's the same as adding all the sigma 1 formulas. And in the case of Boolean algebra, if you add atom, that's the only structural thing you need to add to get all the sigma 1 formulas. And of course, the sigma 1 formulas, these are infinitary sigma 1, so they code zero jump. So you always need to add zero jump. But what is the structural part that you need? In this case, is that. So there are a few other classes of structures where you get such a nice result. You tell? Yeah, I guess for graphs in general. So you don't get them in general. Finitely many predicates. Right. So I looked at that. So there were a few examples where you get finitely many or nice, or maybe sometimes you get, like in the case of double jump of linear orderings, you need countably many. You need like something that says there are n things in between, but it's still nice. So then I looked at the question, when is that you get a nice one? And then you had to formulate that as something uniform for the whole class and on a cone. And it's equivalent to having countably many existential types. When you have countably many existential types, then you get some nice characterization of these guys, of the jumps. And when you don't, then... Okay, so sometimes you get nice characterization of the jump, sometimes you don't. But the jump always exists. Sometimes it's not nice, but it always exists. You just add. Worst case, you add all the sigma 1 formulas. Okay, so and then after that, after those definitions, I guess they continue being studied for quite a while, and then as I said, so some results in computable structures become nicer if you use this vocabulary. So one of the questions that came up later and took a while to answer was, does the jump? Because I mean, we just define the jump. Does it actually jump? So the formulation, what I mean is that question. Is there a structure? Well, I mean the negation of that question, I guess. Is there a structure that is equivalent to its own jump? If it jumps, there shouldn't be. The jump should always be higher up. Okay, so the answer to that question is, well, it depends on what you mean by equivalent, which is good. Okay, so what do I mean by equivalent? So before I was talking about this effective by interpretability. I don't want to get into details of effective by interpretability. So I'm going to look at the simpler versions of equivalence than that are easier to define. One, and I guess the first one that comes up, Steve was asking me, and this is the first one that you thought of. You say that a structure is Muchnik reducible to another structure. A is reducible to B. If whenever you have a real that computes a presentation of B, it also computes a presentation of A. So this is the same thing as saying that the degree spectrum of A is Muchnik below the degree spectrum of B in terms of set of reals. And it's the same thing. I say whenever you're giving a presentation of B, you can use it to compute the presentation of A. And then, of course, from the reducibility, we can talk about Muchnik equivalence. Now you reduce in both senses, which in this case means you have the same degree spectrum. Or you could be in Medvedev. You can look at Medvedev equivalence. In this case, it's a strong reduction. So A is Medvedev reducible to B if there is a computable operator, fixed computable operator, that given a copy of B produces a copy of A. So it's a uniform way of saying this. So you have one way of transforming copies of B into copies of A. All right? Okay, so and then we get an equivalence. So what happens in these cases? So first, if you're looking at Medvedev equivalence, the answer is no. It is so okay. So maybe I messed up here because I asked the question in two different ways here. The answer to the question in blue here is no. So no structure is Medvedev equivalent to its own jump. The reason for that, I didn't write it down, is that if a structure A is Medvedev equivalent to a structure B, then you can prove that the existential theory of A is enumeration reducible to the existential theory of B. Existential theory means a set of all existential formulas true in A and true in B. If you have a one way of producing copies of this from copies of this uniformly, you can get the existential theory of this from the existential theory of that. But then you can show that the existential theory of the jump of A is greater in enumeration degrees to the existential theory of A jump. And here I mean enumeration jump. Then there's the enumeration jump of a set. So when you look at the existential theory of a jump, you must go up. So you couldn't have that an A jump. That A Medvedev computes this one. Because the enumeration jump, the existential theory has to go up in enumeration degree, while it doesn't in the other. That's not true for Muchnik, this thing up here. In the case of Muchnik, what you get is that if A is Muchnik equivalent reducible to B, then there exists a tuple B such that the existential theory of A is enumeration below the existential theory of B together with that tuple. But that doesn't allow you to use these arguments. So this argument doesn't work for Muchnik because you get this tuple. But now if you add a tuple here, to look at this with some tuple, then you might have a bigger tuple here. So it's not the same. So you can show, and this is what we're going to do the rest of this lecture, that there is a structure that is Muchnik equivalent to its own jump. So in this case, it doesn't jump if you look at Muchnik equivalence, at least for this particular structure. Okay, so that's a statement of the theorem that we're going to look at. There is a structure equivalent to its own jump. There are three proofs that I know of these results. The first one, the first two are independent. It uses the existence of zero sharp and builds a model of ZFC plus V equals CFC, plus V equals L, or CFC minus. Okay, I'm not going to go into that. Putsarenko at the same time, also we didn't know if each other's proofs. He builds also an example. He, instead of using 0 sharp, he uses omega 1 ck iterates of the power set axiom. He has to use omega 1 ck iterates of power. And he builds a model of essentially the same thing. I guess he uses kp plus v equals L, but he doesn't use indiscernibles or sharp. So they were similar in the type of model, but very different, so completely different in the way you build the structures. His uses less assumptions. Mine was easier to understand, because if you have more assumptions, you can get a nicer proof, usually. Okay, and then last year, Noam sent me this email that him and Dan Turecki had a new proof of that result. I guess that proof wasn't needed some fixing, and then I changed completely that proof made me think of different ways of proving it, and then I have this other proof that I don't know if it has anything to do with the proof. Well, I guess no, you will tell me if it has anything to do with the original proof. But thinking about it was motivated by that proof, because I was trying to understand what was going on. And then he uses things that were known, like some versions of R-wise compactness, applications of R-wise compactness that were known in the 60s or 70s. So I'll show you this proof. And it was very nice, because he sent me the email, then we said we'll figure out this new proof, and then I was, okay, this is much more elementary than those, it's easier to explain. So let me, in the next few slides, show you what this construction is. Okay? So those are the proofs, and then a separate result the other way around. That maybe if you have time, I'll tell you a bit of the proof, is that you need at least infinitely many iterations of the power set axiom to prove that there is a structure equivalent to its own jump. So the fact that this proves they all use iterates of the power set, I mean, we can prove that you need at least infinitely many. I don't know if you need omega 1 ck. Or I don't know, maybe you can simplify them to use omega many iterates, or maybe you can improve this proof. I don't know, but at least it is a theorem that is not provable in this, where most of mathematics is provable, even though it's about just one jump, being equivalent to one jump. This is pretty much the same theory that I guess Ted was talking about, CFC minus with finitely many iterations of the power set axiom. Even though it's completely different, I don't know. But okay, so the last slide is about the idea to prove this. But let's go to how you build this proof of a structure equivalent to its own jump. Okay, so the structure is not going to be a model of V equals L, so then I don't need to introduce V equals L or CFC. It's going to be a jump hierarchy. But I call this jump hierarchy structures. So it's a structure, it's not a set, it's a structure that behaves like a jump hierarchy, but in this sense of jumps of structures. So it looks like this, has an ordering on the domain. The domain is linearly ordered. And it has all these relations, Rij. And the idea, so Rij has additive j plus 1. And the idea is that this relation is going to be true of A and B1, Bj. So if B1, Bj are below A, so they belong to the ordering, this ordering below A. And if you look at the ordering below A with all these relations, then this Rij is mimicking the ith sigma 1 formula of additive j. Okay, so remember, these are the sigma 1 formulas with additive j all listed, and you look at whether the formula is true all the way up to A, and then that's what you make, that's what you put in here. Okay, so essentially what's going on is if you look at A and all the relations that start with A up here, you're coding the jump of everything that happens before A. Yeah? So the formulas that have A up here are coding the jump of all of the structure up to A. Yeah? Do you guys see that? So I have here is the set A, and they have all these relations. And if you have an A here, if you consider this part, this is J up to A, then this column, all the relations Rij here code the jump of A up to A. So all the previous ones. Okay, so that's what those relations are. So each one is to jump all the previous ones. So it's essentially like a version of the jump hierarchies, but for structures. And well, I guess since it's for structures, you need these parameters. So there is some structural information here. And this is not a presentation. This is an isomorphism type. It's isomorphism types. Okay? So whenever you have that something is successor of something else, J at A plus 1 is it's much more than that. So up to here is the jump of the previous one, right? Because if you have the jump of the previous one, you can figure out this column, this extra value. So every time you go plus 1, you get the jump of the previous one. If, by any chance, you have two elements such that the structure up to A and the structure up to B, so if these two are isomorphic, not isomorphic as linear orderings, isomorphic as jump hierarchies, completely isomorphic. Like this one, if the whole thing is completely isomorphic to the whole thing up to there, then you will get that that this one is equivalent to its own jump because the structure up to here, if you use this guy as parameter, so J up to B, if you use A as parameter, compute in Muchnik way, J up to A jump, because he knows A plus 1, so he knows the jump of that one. And then that one, of course, is Muchnik below J up to A, and that's isomorphic to J up to B. So then you get a J up to A and J up to A jump are Muchnik equivalent. Each one computes the other one, because J up to A is isomorphic to this, which computes A plus 1. Yeah? So from there you will get a structure that is equivalent to its own jump. Okay, but for that we need to find a jump hierarchy and that has two elements such that the jump hierarchy up to here is isomorphic to the jump hierarchy up to there, including all the relations, not just the linear ordering. What we know is that if A is well ordered, then of course we can define a jump hierarchy because at each column for each A, you define this by looking at the structure below A, so you define it just by transfinite recursion. Yeah? Though well orders are not going to have any two elements that are automorphic. Yeah, so that's where the barwise compactness is going to have to come in. Oh, and let me mention, here I don't mean just countable. Even if A is uncountable, you can define this jump hierarchy along A. It's just transfinite recursion. It doesn't matter. It's just all you need to use is that it's an ordinal. Yeah. So for any well order of any size, there is a jump hierarchy with domain A. Okay, so this is the theorem we need to use. And the theorem, so at the end, right, so after playing with the proofs, then at the end the theorems we need was, with the jump hierarchy, it was a new thing, and then this theorem is actually from Morley and Barwise 60s, I think, when they were studying the Hanf number of this logic. It says that if you have a computable infinitary sentence, and it has a model of size Beth omega 1ck, so that means omega 1ck iterations of the power set, then it has a countable model that has a non-trivial isomorphism. They actually get more. They get, if you have a model of size Beth omega 1ck, then you have a sequence of indiscernibles, and then you can have models of any size and automorphisms of any size. The proof for just one non-trivial isomorphism is easier in this case. And you need this. Actually, if you have a model, so there are sentences that have models that don't have models of this size, but have models of Beth alpha for alpha below omega 1ck, and still have no countable structure with a non-trivial. All the countable models are rigid. So you need to go. So in that sense, this is the least cardinal where you get this property, and that makes it what is called the half number of computable infinitary theory. Not exactly, but half number is for if you have models up to here, then you have models from there onwards for all cardinals. And the reason is because once you have the indiscernibles, then you can make models of any size you want. Okay, so what's the proof of that? Okay, so now, it's clear how this implies this, right? It implies what we want. So that theorem is going to give us a structure equivalence to its own jump, because we know there are jump hierarchies of any size, because for every well-ordered there is a jump hierarchy on it. And the theorem is going to tell us that there is one that has an automorphism. So there is one that you have two elements that map, one goes to the other, and then you get a structure equivalence to its own jump. All right? But you need to use that there are with these jump hierarchies up to Beth omega 1ck to get a countable one with an automorphism. Okay, so what is the proof of that theorem? But this is in general. This is for any L omega 1 omega sentence. Okay, so you're going to define, we're going to consider structures of this form. They have the following ingredients. So M part is a model of this sentence phi that we're talking about, the one that we want to build the models for. L is a linear ordering, which you can have to think of a well ordering, but might not necessarily be a well ordering. Maybe non-standard well ordering. That you're going to see later where it comes in. And E is a set of triples, essentially. Has something from the well ordering and two tuples from M. And it's trying to encode these back and forth relations. So for each element of this linear ordering, this that takes two tuples from M is an equivalence relation. So we have a sequence of equivalence relations for the things in the linear ordering. When you put here the first equivalence relation, the one that corresponds to the element 0, that just says that A and B satisfy the same atomic formulas in M. That's the first equivalence relation. You can say that with an infinitary formula. So the first equivalence relation is satisfying the first atomic formulas. And then when you go up L, you look at this back and forth property. So if you have the alpha's equivalence relation is true, I should have put if and only if, for every beta below alpha, for every D that is extends B, there exists a C, such that you have the equivalence relation, and vice versa. For every C, there is a D that you have the equivalence relation. These are what they are called the back and forth relation, right? So your relation at level alpha, if whenever you extend this one, you can extend that one so that you're equivalent at the previous level, and vice versa. So these equivalence relations get finer and finer and finer and finer. And if kind of it starts with just having the same atomic formulas, but then it's like more. I mean, if two things satisfy this relation, it means that they are very similar to each other. It's very hard to distinguish them, because you can extend one, you can extend the other one, you can extend the other one. If A and B were automorphic, then they satisfy this and they satisfy these two because you can always match them back and forth. And E and F, the last part of the structure, are just two elements that are different, but they are equivalent all the way through for all the relations. Okay, so that's what we're going to be looking at. You have M, you have L, it's a linear ordering, and these back and forth equivalence relations on them. And we want also the property that for every alpha that is a computable ordinal, there is an initial segment of L that looks like alpha. So we want alpha to extend omega 1ck. Alpha is going to start like omega 1ck and go beyond. Okay, so let's see how we prove this. So first of all, if L is ill-founded, I didn't say that L has to be well-founded here, then E and F, those two constant elements, must be automorphic. Right, so E and F are two constant elements that are related in this equivalence relation all the way through. If the L is ill-founded, then they must be automorphic. And the reason, this is a little sketch, if you have a set that has, if it's ill-founded, there is a set that has no least elements, a subset of the linear orderings. All the things that are related, irrelated, using some, pseudo-ordinal in this non-well-founded part, these set must have the back and forth property. I mean, if you extend B, there must be an extension of A that also belongs to a set. Because if you're related with something in C and C has no least elements, whenever you just take another element in C that is below, it has no least element, whenever you extend B, you can extend A, so you're equivalent on this thing below. So the back and forth property means that whenever you extend one, you can extend the other one and you stay in the set of pairs. And it means, and whenever you have the back and forth property and you have a countable structure, you can build an isomorphism, right? Because if two things, if you map this one to this one and you extend here, you extend here, you extend here, you extend here, and you build an isomorphism that maps essentially A to B. You can keep on extending. So if you started with E and F being equivalent, being in these sets, you can extend the pair E, F to an automorphism of the structure, mapping E to F. Okay, so if and so that's what. So if we do that, then we get what we want, right? Because what we wanted was a model of phi. This is an M, which has a non-trivial automorphism. E and F are different, and they are automorphic. They will be automorphic. So if we manage to make a model of all these things, where L is ill-founded, then we get an automorphism. We get what we want. Yeah, I don't know. I don't know if they use this proof though. This is my version of this proof. I don't know any way what proof they use. After proving it, went look it up and there was. Okay, so this is what I just said. Okay, so if you have a model of 1 to 8 meaning all these axioms, which is low for omega 1, which doesn't compute the presentation of omega 1ck, then the linear ordering has to be a Harrison linear ordering. Because we said that it must contain initial segments like all computable linear ordering, so it has to start like omega 1ck. But if it doesn't compute omega 1ck, it means that whatever happens later has to be non-well-founded. So if it starts like omega 1ck, but it doesn't compute omega 1ck, it's because it must look like Harrison linear ordering. And if it looks like a Harrison linear ordering, it's ill-founded. And and then we get an automorphism. So all we need to do is to show that, and also if there exists a model of 1 to 8, it's a sigma 1, 1 property. Well, I guess, no, if you get a, yeah, so if you get a model of 1 to 8, no, okay, so let's just say this part. So to be able to get such a model, we can apply barwise compactness. And to be able to apply barwise compactness, we need a model of the previous ones, 1 to 7, that make this true up to a certain computable ordinal alpha. Yeah? So if we manage to be able to get this property up to each computable alpha, then barwise compactness, we can get all of them together. And we can even get one which satisfies this property too. We mentioned that before. So we need to be able to build a model of a 1 to 7 for each L below omega 1ck. Okay. So how do we do that? So if L is well ordered, then there is a structure satisfying all these things, 1 to 6, because each equivalence relation is being defined by transfinite recursion using the previous equivalence relations, beta below alpha. So if you can define recurrence relation up to beta, all the way up below alpha, you can define at alpha, and you define them one by one. So if you have a well ordering, you can easily make a model that satisfies 1 to 6. What you don't know is that there are going to be two elements which are different, but still equivalent for all alphas. That doesn't necessarily need to happen. Maybe you get to alpha and they are all inequivalent at level alpha. Okay, so but what are we gonna do in that case? Well, you have to look at this property. If alpha is well ordered, then the alpha's equivalence relation has at most Beth alpha equivalence classes. And the reason is that, well, E0 has only countably many equivalence classes because it's looking at the atomic formulas that are true or not true. Maybe continue many equivalence classes, maybe alpha 1. And then if you're looking at the alpha equivalence classes of a tuple AB, what matters is what are the equivalence classes of your extensions, right? So if there are Beth alpha minus 1 equivalence classes for alpha minus 1, you're looking at subsets of those equivalence classes. Like which equivalence classes do you have at previous level? So it's what are the subsets of the previous equivalence class you have? More or less? Yeah, so what this says is look at all the equivalence classes, all the BDs that you get from extending one element. There has to be one C in this equivalence class. So what matters to see that these two are equivalent is look at the equivalence classes of the extensions of BD. And they have to be the same as the equivalence classes of the extension of A. So it's essentially the equivalence class is determined by subsets of equivalence classes at the level down. So you're taking subsets at each level. So the number of equivalence classes at most are Beth alpha. So if L is below omega 1ck, there is a structure satisfying all of these because the assumption was that we have a model that has size Beth omega 1ck. So if there are less than that equivalence classes, it has to be two things that are in the same equivalence class and are different, and you get 7, and you get 8 but barwise compactness. Okay, so that's the proof of this theorem, and you do need the omega 1ck iterations of the power set to get this automorphism, which then give you a proof of you get a jump hierarchy that has an automorphism. Any questions? Anything maybe you'd like me to slow down and say a bit better? This is a sketch of a proof, so. Anybody? Steve, you see me? You want to ask? Yeah. So for automorphism, non-trivial automorphism. Thanks. Yeah. So yeah. So for this one, you need that many. So you could there is a sentence. I mean, you can write a sentence in. So suppose you have an ordinal alpha below omega 1 ck. So you can look at elements which are essentially each element, the element at level alpha is a set of things at level alpha minus 1. So like a models of set theory, essentially. So essentially, it's a subset of V alpha in set theory. Each element is defined as a set of elements in the previous one. So you can say extensionality. Two things are equal if this relation, they satisfy the same relation with the things at previous level. And so essentially, the models of these are subsets of V alpha. And each element at level alpha is coded by which elements it has on the previous level. So you can have rigid things of size up to beta alpha. And only it breaks at up omega 1 ck. Because, right, to do that, you need a computable presentation of your ordinal to put in your computable structure. So if you use infinitary, but not necessarily computable, like L omega 1 omega, then here will be Beth omega 1, the Helmholtz number. All right, so we get a structure equivalent to its own jump from that. Let me just say a quick word about the necessity of infinitely many iterations of the power set. This is the statement of the theorem. I guess I'm just stating the same thing I said before. If you take CFC without the power set axiom, but with an axiom that says that you can iterate the power set axiom on omega n times, then that's not enough to show that there exists a structure Muchnick equivalent to its own jump for any x you fix. The proof of this, I can tell you a little idea for the case n equals 1. You show that if you have a structure that is Muchnick equivalent to its jump, then you can build an omega model of second order arithmetic. This is for the case n equals 1, so just one power set. One power set, you have natural numbers and you have reals, so it's the same as second order arithmetic. So if you take all these set x's, which are CE in every copy of A, as your second order part, and you take omega as your first order part, you get a model of second order arithmetic. I mean, you have to prove that, but once you prove that, you will get that if you have such a structure, then second order arithmetic is consistent, because you're building a model. So that means you couldn't prove the existence of the structure in second order arithmetic. For when you go higher ends, instead of the x's that are seen in every copy, you have to look at the sets of reals which you can encode computably in every copy of A. And it gets a bit messier in that case, but it works. And the reason that this is a model of second order arithmetic, I mean, it requires, it's not easy to see, but what's behind it is a theorem of Julia Knight that says that if x is C in every copy of A, then x is enumeration reducible. It's an enumeration operator. It's enumeration reducible to some existential type of some tuple in A. So if you're always CE in every copy, then there is an existential type such that you're irreducible to it. And so that allows you to name every set like this with an index for the enumeration reducibility and a tuple P. So for each tuple P and each E, you have each an X like this. So you have a names for all these X's using tuples and numbers. And then, so you can talk about this structure of second-order arithmetic within your structure A, because now the elements are named by pairs E, P. And if you have a pi 1n formula in this model of second-order arithmetic, it becomes a computable infinitary pi n formula inside A, because you're encoding these sets inside A. But if you can encode a real in a computable infinitary pi n formula, then you look at the nth jump of A, and this real now is sigma 1 definable in the nth jump of A. But the nth jump of A is equivalent to A itself. So that means if it's pi n definable, it's sigma 1 definable and belongs to here. So you can show that this model is closed under pi 1n comprehension, and therefore it's a model of second-order arithmetic. Okay, this all requires work, but that's the idea behind it. And it works for higher-order arithmetic. Okay, I'll stop here. Thanks for your attention. Presentations. Yeah, yeah. That's right. Yeah, that's the same thing. No, same thing.
Well, we don't need our set X to prove that there's a Mooching degree which is equal to its jump. I mean, to me, the jump of Mooching degree would be just the Mooching degree of the problem of finding a jump of some element of the. So if you have a problem that is a set of reals, Mooching degree, and the Mooching degree of that is the problem, represents the problem of finding an element of that set. And then the jump would be the problem of finding the jump of some element.
Yeah, so that's that's interesting. So no, it's not a mistake. And actually, that was part of the reasoning to find. I mean, I remember when I was thinking of this problem. So he said, but the two things. So Steve said, so the Mooching degree of the structure is the same thing as if you look at Mooching reducibility among sets of reals, is the set of representations of the structures. You're just looking at that. If you want to show that there is a Mooching degree such that the jumps of all the, and you take all the jumps of all the elements of it, that set that is equivalent to that, you can show that. There's not going to be hyperarithmetic elements, but with clean ISO, you can build such a thing. So for instance, if you take a descending sequence, a set of reals such that go down and each one jumps to the next, no, you get a descending sequence, each one jumping to the next, which these things exist in below clean ISO, I guess. And take everything above them, then that's going to jump to itself, because you have the descending sequence, you all jump to itself. So use a Mooching degree that is its own jump, and yeah, you only need maybe pi 1 comprehension or something to prove that. But it's not the Mooching degree of a structure. And that one actually we know because, so also another result of Julia is that the degree spectrum of a structure can never be the intersection of countably many cones. Sorry, the union of countably many cones, of all these cones going down. So that one in particular is not a jump of a structure. It's not a degree of a degree spectrum of a structure, which also follows from here. It agrees. Yeah, that's right. Yeah. Well, the difference is that we're looking for a Mooching degree that is equivalent to the degree spectrum of some structure, and that one is not. So if you want a structure, that whose Muchnik degree jumps to itself, it has to be complicated as that one. That's right, yeah. Mm-hmm.
Well, there are only continuum many structures.
Yeah. Right, yeah. It's much fewer, yeah.